Let's first see a motivating example where we are doing linear regression for n data points. We can of course run gradient descent, but if n is too big, people usually run stochastic gradient descent. We just pick a random data point I and go the stochastic gradient direction using the point I. Let's consider a special case. It's not realistic, but very interesting. If all the data points are equal to each other, that means all the SGD direction are equal to the full gradient direction. That means SGD equals GD, but it only needs 1/n computational cost. Another special case is if the first half points are equal to each other and the second half points are equal to each other. That means if we pick 1 point from the first half, 1 point from the second half, then we get the full gradient. In this case, we're sampled SGD equal to GD, but we only have 2/n computational cost. So in general, we notice that the data cluster information can be very helpful. If points are duplicated as S clusters, we can just pick S representatives to get exact full gradient. And that will be n over S times faster than gradient descent. However, in practice, we notice that points are not identical in every cluster, so one representative for every cluster is not enough. We need some adjustment. So we propose two different algorithms to do the adjustment. First one is cluster SVRG. We run SVRG algorithm inside each cluster. SVRG uses following gradient estimation, and one can show that if the points are close to each other for every cluster, then this estimation is almost close to the full gradient. And this is verified empirically. The dual version, in the dual space, the data points are corresponding to the coordinates. Full gradient descent means we will go all the directions together, and coordinate descent means we will go one random direction. But here we have clusters, so we can go to the combined direction. For example, if x and z they are in the same cluster, we can usually go to the combined direction, which is the similarity of x and z. And sometimes we do the adjustment direction, which is orthogonal to the combined direction. And one can show that this algorithm is much faster than the ACDM algorithm, and it is verified empirically. So how do we get the clusters? Using LSH algorithm, we can quickly identify raw clusters, because here we only need very raw information of the clusters. Very good clusters are not necessary for our algorithm.